In this video, we review the notion of divisibility and greatest common divisors. So divisibility is really just a special case of the division algorithm from the last video. It's namely the case when the remainder is equal to 0. So first we'll define what it means for a number to divide another number, or rather an integer to divide another integer. We'll say let a and b be integers, b be positive, and we say that b divides a if there exists a c and z, if there exists another integer c, such that a is equal to b times c. The notation we'll use for this is we'll write b divides a, right? This is pronounced b divides a. If no such c exists, so if we can't write a is equal to b times c, so in the case that a is equal to b times c plus some remainder, we'll write b does not divide a. This is pronounced b does not divide a. So maybe we can look at a few examples. So the first example to look at might be something like 7 divides 56, right? 7 divides 56, since we can write 56 as 7 times 8. And in this example, what I'll try to do is I'll try to keep it into the a is equal to b times c format. I'll try to keep it to this format. So we can see that the integer c that we claim exists is the integer 8. Another example would be -3 divides 27. Why is this the case? Well, 27 can be written as -3, that's our b, times -9, that's our c. So in this case, there exists an integer c, in this case, c is equal to -9, such that a is equal to b times c, such that 27 is equal to -3 times -9. If we look at some other examples, let's say we look at 5 and 11, 5 does not divide 11. Why is this the case? Well, it's since 11 is equal to 5 times 2 plus 1. We actually have a remainder of 1. So the division algorithm tells us that the remainder is 1. And in particular, since remainders are unique and quotients are unique, it's impossible for there to be a remainder of 0. The remainder must be 1. So in this case, 5 does not divide 11, and 11 cannot be written as a multiple of 5. We can also write down some more general statements. For example, we could say if a is any integer, then 1 must divide a. Why is that the case? Well, this holds since a can be written as 1 times a. All right, so in this case, our choice of c is a, and our b is 1. Another thing we can say is that if b is any integer, and let's say b is bigger than 0, then b divides 0. Why is this the case? Well, this is true since 0 can be written as b times 0. So in this example, our c is equal to 0, our a is equal to 0, and our b is just equal to b. We can also prove some general statements, and so I'll prove some general facts that we'll be using and referencing, and these are going to be very, very quick proofs. So the first thing we'll prove is that b divides a if and only if -b divides a. And again, our assumptions on b and a are the same. We're assuming that b is non-zero, or rather, b is non-zero, and we're assuming that a is an integer. So let's prove this. So let's say b divides a. Well, what does this mean? This is true if and only if there exists an integer c and z such that a is equal to bc. And we're going to take this equation and rewrite it. We'll say, well, this means that there exists an integer c and z such that a is equal to -b times -c. So now what have we done? We've written a as -b times another integer. If c is an integer, then -c is an integer. And what does this tell me? This tells me that -b has to divide a as well. One more observation we can make is the following. I'll say, suppose, so if b divides a and a is non-zero, then the absolute value of b is less than or equal to the absolute value of a. So this is a quick proof as well. This is a proof by contradiction, so I'll say suppose not. So I'll say suppose that b divides a is non-zero, and the absolute value of b is strictly larger than the absolute value of a. Well, where does this lead us? Well, let's look at our assumptions. Our first assumption is that b divides a. So I'll say since b divides a, we know that there exists an integer c such that a is equal to b times c. Okay, where does that lead us? Well, we need something about absolute values, right? I need to talk about the absolute value of a and the absolute value of b. So this leads me to say then the absolute value of a is just the absolute value of bc. And this can be rewritten as the absolute value of b times the absolute value of c, just using standard properties of the absolute value. Okay, so we have something here. Now, let's apply this to our inequality. So we haven't touched this inequality yet. So let's see if we run into a problem when we apply this. Well, then we arrive at the absolute value of b is bigger than the absolute value of a. And now we know the absolute value of a is equal to absolute value of b times absolute value of c. And the one thing to notice here is that since a is non-zero, neither b nor c is allowed to be 0, right? B is non-zero by assumption. I'm not allowed to divide by 0. And c is non-zero because if c was 0, then a would be 0. So we know that b is non-zero and c is non-zero. So in particular, I know that the absolute value of c is either 1 or larger, so that this number right here is greater than or equal to the absolute value of b. So what does this lead me to? So I could say then the absolute value of b is greater than the absolute value of b. And this is a contradiction. This is not possible. So hence, we can conclude that the absolute value of b is less than or equal to the absolute value of a. So that concludes our proof here. This does have one important corollary. So really quick corollary, really quick consequence. If a is already positive, then the absolute value of a is a. So I'll say if b divides a, and a is bigger than 0, then b is less than or equal to a. So we'll be using this fact quite a bit as well. Another thing we need to discuss is the notion of common divisors. So let's look at two numbers that I've pre-selected. So let's look at the divisors of 42. So what are the numbers that divide 42? After we think about this enough, we'll get plus minus 1, plus minus 2, plus minus 3, plus minus 6, plus minus 7, plus minus 14, plus minus 21, and finally plus or minus 42. So these are all the divisors of 42, all the integers that can divide 42 according to our definition. We can also ask ourselves, well, what are the divisors of 36? And we can make the same list. We could say, okay, 1 and -1 always divide any integer. Plus minus 2 is a divisor of 36. Plus or minus 3 is a divisor of 36. Plus or minus 4. Plus or minus 6. Plus or minus 9. Plus or minus 18. Whoop, I think I forgot one. Plus or minus 12 comes first, then plus or minus 18, and then plus or minus 36. Right? And then we can ask ourselves, what are the common divisors? What divisors do these two numbers have in common? Well, we see that plus or minus 1, they have in common. Plus or minus 2, they have in common. Plus or minus 3, they have in common. Plus or minus 6, they have in common. And then that's it, right? So we can say, what are the common divisors? Well, if I write down the common divisors here, we get plus minus 1, plus minus 2, plus minus 3, and plus or minus 6. Those are the only divisors those two sets have in common. And we can ask, well, among those common divisors, what is the largest common divisor? We're going to call this the greatest common divisor. So the greatest common divisor is very easy to pick out here. The greatest common divisor is going to be 6. It's the largest number that divides both 36 and 42. And so this is going to motivate our definition for what's called the greatest common divisor. It's going to be, if I look at two integers a and b, let's say they're not both 0, so one of them has to be non-zero, I can write down their divisors and say, what is the largest number that divides both of them? What is the largest integer that divides both a and b? So we'll use this as our motivation for our definition of greatest common divisor. So we're ready to write down our definition of greatest common divisor. So we'll typically call it a GCD. So a lot of times it's shorter to write GCD rather than greatest common divisor. So throughout these videos, I'll be writing GCD. It's a pretty universally understood way of writing greatest common divisor. But what is the greatest common divisor? Well, we know it has to be an integer, and it's somehow associated to a and b. How is it associated to a and b? Well, it has to satisfy two conditions. It has to satisfy the condition that, well, first it has to be a common divisor. So d has to divide a and d has to divide b. And we want to capture the word greatest in here. So let's think about how to do this. So we'll say if c is an integer and c divides a and c divides b, then we must have that c is less than or equal to d. So this is capturing the condition that d is larger than every other common divisor of a and b. So a common divisor is a number, again, that divides both a and b. So in this case, c is an example of a number that divides both a and b, and we're saying that d has to always be greater than or equal to c. We'll set up this notation we'll use the notation, we'll write the GCD as an ordered pair, right? Just A comma B. And if the GCD of A and B is 1, we say A and B are relatively prime. Right, so in some sense, this is capturing the notion that they have no common factors besides 1 and -1. Okay, so let's look at some examples. We saw earlier that the GCD of 36 and 42 was equal to 6. We can look at, well, what is the GCD of 3 and 7? We could think about this for a bit. We'll see that the greatest common divisor of 3 and 7 is equal to 1. We can ask, what's the GCD of, let's say, 10 and 32? And if we think about this for a bit, we'll see that the GCD is 2. So we can stare at this for a little bit and kind of play around with GCDs, kind of think about how to compute them. There'll be an upcoming video about how to actually compute GCDs without going through this cumbersome process of, you know, writing out all the common divisors and then picking the largest one. That's really cumbersome and tedious and horribly inefficient. So there'll be a video about this in a little while. But what do we notice about these numbers? Well, we could stare at these and we might notice that, wait, I can always write 6 as 42 times an integer plus 36 times another integer, right? And I might fill in these blanks and I might say, okay, the blank here is 1, 42 times 1, and 36 times -1. So I could fill in these blanks. I might look at this and I might say, oh, maybe I could do the same thing with 7 and 3. So I might stare at this for a little while and convince myself that 7 times 1 plus 3 times -2 is equal to 1. I can look at 2, the GCD of 10 and 32, and ask myself, can I write 2 as a multiple of 32 plus a multiple of 10? And let's try to fill in these blanks here. So here we could say this is going to be 32 times 1 plus 10 times -3. Right, so this will give me 32 minus 30, which is equal to 2. So this leads us immediately to what's called Bézout's lemma. And Bézout's lemma is the statement that if A and B are two integers, not both 0, so one of them is allowed to be 0, and D is their GCD, then I can write D as what's called an integer linear combination of A and B. So this just means that, so this leads us pretty naturally to what's called Bézout's lemma. And Bézout's lemma says the following. It says, let A and B be integers that are not both 0. So we're allowing the possibility that one of the integers is 0 as long as the other one is non-zero. And let D be the greatest common divisor of these two integers. Bézout's lemma then says that D can be written as what's called an integer linear combination of A and B. And what does this mean? This just means that there are some integers U and V that allow us to express D as AU plus BV. And one thing we'll see is that U and V in this theorem are not unique. So there's no uniqueness portion to this theorem. There's just an existence portion. So let's begin the proof of this theorem. And the proof is going to use the well-ordering principle. So I'm going to set up a set. I'm going to say let S be all the numbers that can be written as integer linear combinations of A and B. And the ones that I'm interested in particular are the ones that are positive. So AM plus BN is positive. So I've set up a set that's a subset of the naturals. And I'd like to use the well-ordering principle here. Well, step one, in order to use the well-ordering principle, I have to show that S is not the empty set. So I need to produce a choice of M and a choice of N that guarantee that AM plus BN is in that set. I need to just guarantee that AM plus BN is positive. So what am I going to do? I'm going to say let M equal to A, N equal to B. Then if I look at AM plus BN, well, this is just going to be A squared plus B squared. And now, since I know at least one of those numbers is non-zero, I can say that this is positive. So I know that either A squared is positive and B squared is positive, or maybe they're both positive. And I get that this is bigger than 0. And this leads me to a conclusion that hence A squared plus B squared is an element of S, and S is not the empty set. So what does this allow me to do? Well, by well ordering, now that I know that this set is non-empty, by well ordering, oh, let me fix that typo. I can say S has a smallest element, and I'm going to claim, well, I'm going to give that element a name first. Let's say T is equal to AU plus BV for some U and V and Z. All right, so this is going to be the smallest element of S. This is the smallest number that occurs inside of S. So we're going to now claim that this number T, the smallest element of S, is actually the greatest common divisor. So we need to show two things. We need to show, one, that T divides A and T divides B. And two, if C divides A and C divides B, so we'll assume C is an integer, C divides B, then C is less than or equal to T. So we need to show these two parts. Okay, so let's begin our proof of that. Well, the first thing we can say is, since we're not sure if T divides A or not at this point, we could say that by the division algorithm, there exist integers Q and R, so a quotient and a remainder, satisfying the following, such that A is equal to TQ plus R, and R is bigger than or equal to 0 and less than T, right? And our goal here is to show that R is equal to 0, right? Our goal is to show that the remainder is 0, so that in fact T does divide A. Well, let's rewrite the statement. Let's kind of inspect this. We have that I could write R as A minus TQ, so I'm just rewriting this equation, and we have an expression for T, right? We said that T was equal to AU plus BV. T can be written as AU plus BV. That was our T from earlier. It's our smallest element of our set S. And we can kind of shuffle this around a little bit and rewrite R as the following. We could say R is A times 1 minus QU plus B times negative VQ. So we have an element of R. And the thing to notice is, well, if R is bigger than 0, right? So if the remainder is non-zero, then R is equal to A times an integer, so A times 1 minus QU in particular, plus B times minus VQ. This meets the criteria of being an S, right? So this guy right here, this number, if R is bigger than 0, then this number is bigger than 0, and this implies that R is an S, and R is less than T. But this is no good, because we said T was the smallest element of S. Right? There are no elements in S that are smaller, so this leads us right away to a contradiction. So hence, we can conclude that R must be 0. That's the only option that's left for us with this remainder. R cannot be positive. So we must conclude that R is equal to 0, and A is equal to T times Q. In other words, i.e., T divides A. And we can also say that similarly, same exact proof, just replace all the A's with B's, T divides B. We now need to show part 2, and part 2 is a little bit simpler. So I'll say, suppose that C is some integer, and C divides A, and C divides B. Well, using our definition of divisibility, we know that there exists integers J and K that allow us to write A as C times J, and B as C times K. All right, so that's just our definition of divisibility at work. And then let's take a look at T. So then we know that T is equal to AU plus BV. And what do we know? Well, A can be rewritten as CJ. So AU is CJU, and B can be rewritten as CK. So this is CKV. And then we might notice that C times JU plus KV is how we can rewrite that statement. What does this tell me? So I could say, hence, C has to divide T. And one thing we might notice is that the greatest common divisor is always positive. So 1 is always a divisor, and our greatest common divisor of any two integers has to be bigger than or equal to 1. Since 1 is always a common divisor, the GCD has to be bigger than or equal to 1. So hence, C divides T, and we know that T is positive. So we can conclude that C has to be less than or equal to T, and this finishes our proof of Bézout's lemma. And one thing I'll note here, one observation. So note, not only is the GCD a linear combination of A and B, it's the smallest positive linear combination we can make with A and B. So A comma B, the GCD of A and B, is the smallest positive number we can express. It's the smallest positive number that's expressed as AU plus BV. So this is the smallest positive number. It's the smallest element in that set S. So oftentimes it's useful to use an alternate definition of greatest common divisor, and I'll kind of explain what we're going to be doing here. So on the left-hand side here is our usual notion of greatest common divisor in the integers, right? So this is just the same conditions from earlier in the video. And one thing that I want to point out is in a ring, we'll see later on that the idea of divides makes sense, but the idea of less than or equal to, what it means for one element to be less than or equal to another one, won't always make sense. So what we'd like to do is to come up with a definition of greatest common divisor, or some statement that's equivalent to the definition of greatest common divisor that uses divisibility rather than inequalities. So we're going to prove the following theorem. So we'll assume that A and B are integers that are not both 0 and D is a positive integer. We're going to show that D, being the GCD of A and B, is equivalent to conditions alpha and beta. And so condition alpha probably looks familiar because condition alpha is just the same as condition 1 on the left-hand side. But condition beta is a little bit more friendly in terms of divisibility. It says if C divides A and C divides B, then C divides D instead of the C less than or equal to D condition. Okay, so let's begin our proof, and the proof is pretty straightforward. So one thing we see right away is that condition, so we want to assume, so I'll say suppose that D is the GCD of A and B. By definition, we can already say that condition alpha holds, right? We'd like to show that if D is the GCD, then condition alpha and condition beta are going to hold. So condition alpha holds because condition 1 holds. So what we really need to show is that condition beta holds. So let's do that. So we can say that since D is the GCD of A and B, there exists integers U and V such that D is equal to AU plus BV. Okay, so what am I going to do to show that condition beta holds? I'm going to say let C be an integer such that C divides A and C divides B. I want to show that C has to divide D, right? My goal is to show that C has to divide D. Okay, well, I'll say then there exists integers J and K such that A is equal to Cj and B is equal to Ck. So what can we conclude? We'll say that then D, which we've written as AU plus BV, can now be written as, well, I'll replace A with Cj, so this is CJU, and I'll replace B with Ck, so this becomes CKV, and we see that this is just C times JU plus KV. And what does this tell me? I could say hence C divides D. So D is a multiple of C. So this proves condition beta. So I could say, and so condition beta holds. Okay, so that's the first half of our proof, and we'll see in a second that the second half is even quicker. It's even easier. Okay, so for the backwards direction, I'll assume D is an integer that satisfies condition alpha and condition beta. And what we would like to do is show that as a consequence, D must satisfy conditions 1 and 2 in order to be the GCD. So let's do that. Well, since alpha holds, so does condition 1. So this is trivial, right? Alpha and 1 are the same thing. So we've shown condition 1 holds. We need to show now that condition 2 holds. So I'll say, suppose that C is an integer and C divides A and C divides B. Then by condition beta, we know that C divides D. Since GCDs are always positive, so I could say since D, well, not GCDs are always positive, since D is positive by assumption, we have by an earlier result in this video that C is less than or equal to D. And so condition 2 holds. Thus, D is the GCD of A and B. Okay, so that finishes our recharacterization of the greatest common divisor. So the last thing we're going to prove is this neat little proposition. It's a very useful fact. We'll be using it when we talk about integers quite a bit, but it's also a nice exercise using some of the results from this video. So we're going to assume that A, B, and C are integers and that A divides B, C, and that the GCD of A and B is 1. So that so we're saying A and B are relatively prime, or in other words, that A and B have no common factors. This proposition says that A must divide C. Okay, so let's prove this. So let's look at our assumptions. We know that A divides BC. So I could say since A divides BC, there exists an integer J such that BC is equal to AJ. And I can also look at my GCD and apply Bézout's theorem. So I could say since the GCD, or rather Bézout's lemma, since the GCD of A and B is 1, there exists integers U and V such that AU plus BV is equal to 1. And I might stare at this for a while and notice that this equation I've written down, this AU plus BV is equal to 1, doesn't have any C's in it. And so I might try to introduce C's and hope for the best. So my first thought would be, well, let's multiply both sides of this equation by C. So let's see what happens when we do that. We'll get CAU plus CBV is equal to C. And we can rearrange these. So I can write this as ACU plus BCV is equal to C. And then I might notice that, wait, I know what to do with BC. BC can be replaced with AJ. So let's do that. I'll write this as ACU plus AJV is equal to C. And then I notice that an A can be factored out of the left-hand side. So I'll write this as A times CU plus JV is equal to C. And what do I get? Well, I can conclude, so I could say hence, A has to divide C. And that's going to prove our result. Okay.